And step 1, row reduction. We start by simplify each row. For every row, we find the smallest number, and then we subtract that smallest number from every other number in the same row. This helps make sure each row has at least one zero. For job 1, the smallest number is 2. We subtract 2 from every number in that row. The row changes from 8, 6, 2, and 4 to 6, 4, 0, and 2. For job 2, the smallest number is 6. We subtract 6 from every number. The row becomes 0, 1, 5, and 4. For job 3, the smallest number is 3. After subtracting, the row becomes 0, 2, 4, and 3. For job 4, the smallest number is 5. The updated row becomes 0, 5, 7, and 4. Step 2. Count reduction. Next, we simple each count in the same way. For every count, we find the smallest number in that count and subtract it from every number in that count. This step ensures that every count also has at least one zero. In count 1, the smallest number is already 0, so we don't need to do anything. In count B, the smallest number is 1. We subtract 1 from every number in this count. The count changes from 4, 1, 2, and 5 to 3, 0, 1, and 4. In column C, the smallest number is already 0, so we leave it unchanged. In column D, the smallest number is 2. We subtract 2 from each number in that column. The column changes from 2, 4, 3, and 4 to 0, 2, 1, and 2. And step 2, cover all 0 with minimums. Now we try to cover all the 0 in the matrix using the smallest number of straight lines. The lines can be either horizontal or vertical. If the number of lines is smaller than the number of rows, we need to adjust the matrix and try again later. In this case, we can only use 3 lines to cover all zeros, but we need 4, so we go to the next step. Step 4. Adjust the matrix. Now we found the smallest number that is not covered by any of the lines. Then subtract the number from every element that is not covered by any line. Add that same number to every element that is at the intersection of 2 lines. Leave all other numbers unchanged. After doing this, we get a new matrix where we can try covering the zeros again. And step 4, cover zeros again. This time, we try again to cover all the zeros using straight lines. If we can cover all the zeros using the same number of lines as there are rows, then we can move to the final step. In this case, now we can using 4 lines, so we are ready to assign the jobs. And step 6, make final assignment. Now we assign each job to the worker. We look for rows for corners that have only one zero, assign that job, then remove the row and the corner from the matrix. We repeat this until all jobs are assigned. So job 1, only zero in that row, save assignment. Job 2, job 1 worker is C. Job 2 worker is B. After removing corner, C says corner, B is the only option. Job 3, worker is D. A and B are already taken, only D left. Job 4, worker is A. Only one left for job 4. So the last picture is the final result. Total cost is 20. Thank you.
Thank you, Mr. Jing Song, for your presentation just now. So to continue on, I will be presenting on sequencing for two work center. So as you can see on the screen right now, I have chosen one sample problem for us to go through to understand the Johnson rule, which is sequencing for two work center. So this question is a sample question that I sampled it from a Gupta and Star Production and Operation Management System textbook CRC Press. Okay, so now let's go through the questions. So this problem, they are asking for three question, which is number one is what is the order of processing the jobs using the Johnson rule for the table, data inside the table. And number two is what happen if you add another job inside the table, what will the Johnson rule looks like. And number three is draw the Gantt chart for this table. Okay, so let us go one by one. Okay, so question number one, what is the order of processing the job using Johnson rule? So as you can see right now that there's 5 jobs inside the table, but we need to do 5 jobs there. And then there's 2 machines that we need to do. So this is the basic for Johnson rule right now. So first thing first that you need to configure 5 slots. So each of these slots represent the job because we need to rearrange them accordingly based on the shortest processing time in step 2. So right now in the table, we can see that D has the shortest processing time, which is 2 days on machine 1. So what do we do with this information? So since D is on machine 1, we should run it first. So it will be on the left. We put it on the left because it will be run first at machine 1, D. Then we go to the next shortest time after D, which is B. 4 days on machine 1 as well. So inside the table just now, we need to put B next to D. Okay, then repeat again to the next shortest time after D and B, which is E. 5 days on machine 2. Now, D and B is on machine 1, so that's why we put it to the left. But E is on machine 2, so we need to put it on the right. So DB dash dash E. Okay, so now these 2 space remaining, we know that there's A and C left. And looking at the table, we know that A will be on machine 1, shortest time on machine 1, and C have the shortest time on machine 2. So we know now the table will be DBACE. So this will be the Johnson rule for the question number 1. DBACE. Okay, now let us go to the next question. What happened if you add job F to the table in problem 1, which takes 2 days on machine 1 and 1 day on machine 2? So again, same concept. So now there's 6 jobs, so we need to make 6 slots. Okay, so now which job has the shortest processing time? So from the class, we know that's going to be F, 1 day on machine 2. So since it start on machine 2, we put it to the right, F. Okay, then what's next? After we take out F, what's next? It will be D, 2 days on machine 1. So take out D. What's next? It will be B, 4 days on machine 1. Then we took out B from the equation. What's next? It will be E, 5 days on machine 2. Okay, then we take out E. Then again, A on machine 1 is the fastest and C is faster on machine 2. So the full answer will be DBACEF. So that's how we do the Johnson rule. Okay. So now the question number 3, draw the Gantt chart to find the value of max span, but using the sequence of A, B, C, D, E. So meaning it's not following the Johnson rule sequence just now. This is first come, first serve. So sorry. So it's quite simple actually. So we just need to draw accordingly. So now we said start with A first on machine 1, right? So A is 8 days. So 8 days. Plot until 8 days. Then 12 days on machine 2. So you plot another 12 days on machine 2, which total to 20 days. Then you do the same for machine B. 4 days on machine 1, 9 days on machine 2. C is 11 days on machine 1, 7 days on machine 2. D is 2 days on machine 1, 6 days on machine 2. E is 10 days on machine 1, and 5 days on machine 2. So overall, we need 47 days to run this. Okay? And machine 1 job is completed in 35 days. And the idle time is 19 days. So we have 8 days for machine 2, where we need to wait finish processing on machine 1. And we have 11 days on machine 1 where nothing is running because everything now is running on machine 2. Now, obviously, in actual real life condition, the management of the engineering will load another process during that time. But for this case, we just refer it as idle. Okay, so now, yes, that's about it. Thank you for watching. I hope this helps. Bye bye.